So I'm going to tell you about some work in progress that's half done and hopefully not just half baked. And but since this was called a workshop, I guess I thought it would be all right to talk about something that's not finished yet. So let me start by recalling some of what Dan Harlow explained yesterday about the Lorentzian analysis of the 2D dilaton gravity. So to summarize a little bit where he went, so if you look at this nearly ADS2 black hole, it has a two-dimensional phase space. A very simple way of parameterizing that phase space is just by the value of the dilaton at the horizon and the relative time shift between the two boundaries. And total energy is just a simple function, just the square of the dilaton at the horizon. And by the relative time shift of the two boundaries, it's a thing that Daniel explained yesterday. So there's some intrinsic time variable on the two sides, and I can shift the origin of time on one side relative to the other one. So that gives me a 2D phase space. And another way you could try to characterize, another set of coordinates on this phase space that one might like better because it seems more instantaneous, is the length of the spatial geodesic that connects the two t=0 points on the two boundaries, or the two same time points on the two boundaries, and its canonical momentum. So that guy, if we start in the past, is large because the geodesic goes through the black hole and nearer to the singular, and then as you evolve in time, eventually the space-like geodesic that connects the two boundaries will cross the bifurcation point. That's when it has the minimum length, and then it grows again as you go to the future. So in that second set of variables, so the length looks something like this. This is a formula. In the nearly ADS2 limit, so this is just some constant. This is the value of the dilaton at the ADS boundary, or the nearly ADS boundary. This is the dilaton at the horizon, and this t is this time shift variable. So you can see that the time evolution looks the way I described. So we start at t goes to minus infinity. This term is very big. At t=0, it's the minimum value. Then the length of this geodesic is just given by this part, and then it grows again. So it looks like the quantum mechanics of some quantum mechanics scattering problem in this L variable. So the Hamiltonian is simple in terms of this phi h. To rewrite it in terms of this L and its canonical momentum is a complicated expression that I won't bother to write down. But the point is that it looks like some scattering system. So this L variable comes in from infinity, it gets repelled by a potential, and it goes back out to infinity again. But it doesn't look thermal. It doesn't seem to have any entropy interpretation. It has a continuous spectrum of the Hamiltonian. Okay. But there is a nice state, which is the thing produced by the Euclidean path integral on the half disk. Yeah.
Which you don't know how to do, right? Where you look at the factorization into the actual
You mean this expression, or
effective way of capturing the data of the micro?
True, but this is just a particular variable. You don't have to study this length of the geodesic, but that observation might be interesting for something, but I'm not sure what it implies. Yeah. This L is not the Hamiltonian, right? This is just some particular function on phase space. It's the spatial. It's like the size of the spatial slice, the length of the spatial slice.
And it's all right. So suppose we consider pure consignment theory on the two-sphere times time. So that system.
Okay, but you can look at a particular state, which is the state in the 2D gravity language that you get by doing the Euclidean path integral on the half disk. So half of the thing that we might want to call the thermal partition function. But here it just looks like a particular state in this quantum system. It's one of these scattering states. Okay, and Daniel wrote down the wave function of that state, I think, yesterday. Now, how does this relate to how does this relate to something that seems thermal? Well, if you looked at from the dual CFT point of view, or here the let's say we look at it from the dual SYK model point of view, I have one-dimensional quantum mechanics, and I have two decoupled copies of that quantum mechanics system. And then if I did the Euclidean path integral on the half line, in other words, on a half circle, in other words, on an interval, it would produce the thermophile double state in these two decoupled copies of the SYK model. And if I do the path integral on a complete circle, that is some thermal partition function, and I would associate to the whole story an entanglement entropy. So I have two decoupled copies of SYK in the thermophile double states. The entanglement entropy of one side with the other is just the thermal entropy. So that's why you might have thought there should be some entropy interpretation. And you can see what the states that we're talking about in this 2D gravity analysis are associated to in that language. So if I wrote the thermophile double state, it's this sum over energy eigenstates of the left and right system, weighted by e to the minus beta e over 2. And then if I evolve it in time for a while, I pick up this phase factor e to the ITE. So this t is this time shift that I was mentioning, and beta is the temperature, which is related to the value of the dilaton at the horizon. So the bulk Hilbert space is basically the subspace of the full tensor product of the two SYK Hilbert spaces, which is spanned by these states. Now, of course, in this analysis, I'm only keeping track of the pure dilaton gravity degrees of freedom. I'm ignoring anything else that might be in the bulk, so perhaps I shouldn't say it's an analysis really of the SYK model, because that's dual to something more complicated in the bulk, but it's supposed to capture this part of that story. Okay, but now of course, this set of states has some funny property. If I evolve in time long enough, I might start to see the discreteness of the spectrum, the fact that in the dual quantum system, there's actually a discrete set of eigenvalues, and that is the fact that there's a discrete, so that spectrum is crucial to the fact that there is some entanglement entropy, which is a finite and well-defined number. It's something like the density of states at energy associated with this temperature in the grand canonical ensemble. But that would mean that there's some quasi-periodicity in this time shift variable, and that's just invisible in the gravitational analysis here. You don't see a quasi-periodicity in Lorentzian time in the solution. So presumably the 2D dilaton gravity description just breaks down at some time scale before you start to see that quasi-periodicity. So in other words, I start with a state I understand, and if I evolve it long enough, there are rare events that might make me not know what's happening. Maybe it takes me outside the domain of validity of just that gravity description. But anyway, the subspace that we're talking about here is this subspace of of a tensor product Hilbert space, let's say. But the subspace generated by these guys doesn't look like a tensor product, especially since we should restrict the range of this t variable appropriately.
Yeah. Okay, so now, of course, in continuum quantum field theory, there actually doesn't exist such maps. It's not possible to find such a map.
Yeah, exactly. Yeah. Like e to the s kind of timescale.
So you need to regularize the story a little bit. So
well, that's when you would see that. So you wouldn't see, to see periodicity, you have to go e to the s, but you will start to see that the overlap between these states doesn't decay, as a Gaussian by time e to the s, because it will saturate at a value of e to the minus s, something like that. Okay, so here we didn't. So in this nice quantum mechanics, it's perfectly well-defined quantum mechanics, and you have a nice state in it. It just doesn't seem to have a manifest entropy interpretation. Okay, and it's some subspace of a factorized space, but in the subspace, it doesn't look factorized. Well, that's a way of saying that, let's say it a different way. So, okay, so if you want to compute an entanglement entropy or reinterpret it as an entanglement entropy in the Lorentzian Hilbert space sense, you need some way to factorize the bulk Hilbert space in order for that to make sense. Now, of course, if we had the complete theory in the bulk, whatever it is, string theory or the exact theory of quantum gravity, the way it would work is that you would have an exact description of all of the black hole microstates. And then there would be some ER equals EPR type duality between an entangled sum over disconnected microstates and the connected geometry that we're talking about here, that Daniel discussed yesterday. Okay, so that's how it would work in the exact description, and then the Hilbert space would be identical to the Hilbert space that you would talk about in the boundary description, because you would be using the exact theory in the bulk. Now, we don't know what that is, and even in higher dimensions where we know the gravity dual of n equals 4 super Young mills in great detail, we don't have a description of the black hole microstates where we can see the ER equals EPR duality in the bulk language and compute the entanglement entropy in the bulk in that sense. So one might ask, is it possible that there's some effective description? Yeah.
But for this argument, you don't imply that the microspace need be geometric.
Sorry, I actually couldn't hear
you. You don't require the microspace be geometric in any real sense.
No. No, not geometric. The point here is that the microstates aren't geometric. They're something that's not part of this 2D dilaton gravity. In the 2D case, it's completely clear that you can't have the microstates because, the spatial direction is one-dimensional, and so, an interval has, you can't have a one-dimensional thing with only one boundary, right? What do you do on the other side? So there's no, the one-sided system seems impossible to understand just in the pure dilaton gravity. So not only do you not have the black hole microstates, in that case you don't even have the vacuum, right? And in higher dimensions, like let's say we're talking about ADS3 in the BTZ black hole, if I studied pure gravity around BTZ, I'll have just the boundary gravitons. So I have the vacuum and boundary gravitons, but those are irrelevant for finding the entangled microstates you would need to factorize the BTZ spacetime. So again, we don't seem to have it, but in this 2D case, it's the most clear that it's not there. Yeah. Okay, but nevertheless, is there some way to see something? And of course, the main motivation to look for such a possibility is that, it's basically the original surprise of black hole entropy. The fact that black hole entropy is correctly computable from the Euclidean gravity path integral in a regime where it's dominated by some Euclidean saddle that's in the regime of validity of the long-distance effective bulk theory. So in other words, it's some saddle with low curvature. The horizon becomes a smooth point, and the interior is gone in the Euclidean saddle, and so you can evaluate the on-shell action and get the right answer. And so that means that maybe there is some hope that there could be an effective way of calculating at least the entanglement entropy from in the low energy bulk language, but you need some extra ingredient, obviously. Now, if we look at, and this is true in higher dimensions as well, but let me focus on this 2D case. So the 2D gravity Euclidean path integral, the thing where I have the disk, it looks like a hyperbolic disk, that Euclidean saddle, which gives me the correct thermal partition function, say, as an approximation to the thermal partition function of the SYK model. It didn't look like a thermal partition function from the point of view of this Lorentzian analysis, but it doesn't seem to have the interpretation of a trace because the Euclidean time circle shrinks in the interior, which is also the reason why the saddle existed and could get the right answer, but paradoxically it seems to obstruct its interpretation as a trace over something in the bulk language. And again, the Euclidean partition function looks more like I'm just computing the normalization of the Hartle-Hawking type state that Daniel talked about yesterday. So again, that doesn't seem to be an entropy. It actually seems to be physically meaningless. Just a normalization of some Euclidean thing. But the natural idea is to try to introduce some fictitious boundary, if you like, that excises the extremal point. Extremal point meaning the point in the solution which is the Euclidean continuation of where the horizon was. So it's the place where the dilettante sits at its extremal value. In a more general situation, so here I'm phrasing the discussion in terms of the thermofield double state, but a more general scenario would be one where on the half line, on the half circle, in other words, on the interval, or in other words, the boundary of the half disk, I put arbitrary sources that doesn't have to, I didn't have to set the boundary value of the dilettante to be constant in time, for instance, in Euclidean time. I could do something else that would create a more interesting state than the thermofield double state. And then the entropy I would be talking about would be an entanglement entropy. It wouldn't have any thermal entropy interpretation in that case because I wouldn't be getting the thermofield double state. I'd be getting some other entangled state between the two sides. And so in general, the point will not be the Euclidean continuation of the horizon. It might be a point, in other words, I might have a configuration with a long wormhole, and then the extremal point will be somewhere inside the horizon, space-like, to both boundaries. But that's still the point where in the Euclidean saddle, the time circle shrinks. Okay, now, maybe it sounds a little bit weird to try to introduce some fictitious boundary in order to describe the entanglement entropy. What's the point of this fictitious boundary? And I'll try toward the end to relate, to give you a brief explanation of what it might mean from the point of view of having done the exact analysis, which we don't know how to do, of course, where you look at the factorization into the actual microstates. But it should be something like an effective way of capturing the data of the microstates from the exterior point of view. Of course, it will not make sense to get the exact dynamics or the exact spectrum in that way, but the entanglement entropy is a coarser quantity, so maybe there's a way of getting that number at least. But in order to motivate a little bit this idea of putting a boundary there, let me give you a field theory analogy that will also be, I think, interesting in its own right. So suppose we consider Purich-Simon's theory on the two-sphere times time. So that system isn't very interesting because it has a one-dimensional Hilbert space, which obviously doesn't factorize in any non-trivial way. On the other hand, the entanglement entropy of the one hemisphere of that S2 with the other one, it's supposed to be, for Abelian Chern-Simons theory at level k, minus 1/2 log k, up to some, plus some divergent piece that's typically removed. But this number sounds very strange because the Hilbert space here is one-dimensional, so why isn't the entanglement entropy 0? Because I factorize the 1D Hilbert space to tensor product of two 1D Hilbert spaces. Also, if I think of it as a thermal, I can try to think of it as a thermal partition function because the theory is topological, so it doesn't matter whether it was a Rindler horizon or a random surface. And because the theory is topological, you would have thought that the Hamiltonian is trivial. And so therefore, if there was an entropy interpretation, the answer should have been the trace over some Hilbert space, which you would have thought would make the partition function be an integer, but 1 over the square root of k, which is the associated partition function, isn't an integer, so it also seems a little bit peculiar. Now, there's actually an extremely simple way to derive this and give it a entropy interpretation, which is probably well known, but it wasn't so well known to me. The way I'm going to phrase it wasn't obvious to me, but probably well known. So in order to define entanglement entropy, you need to factorize the Hilbert space in some way. So imagine something like this. There's a paper of Tachikawa and a collaborator where they discussed some idea of this type some years ago, and many other people, of course. So this map that factorizes the Hilbert space should be what's called an isometry. In other words, sort of unitary on the left. So if I act with the map and then act back, I should come back to the same state that I started with, so it preserves the inner product. It doesn't have to be an actual unitary map because this Hilbert space might be bigger than this one. And that's perfectly fine. So if you don't have this property, I can just get any answer I want. So what I'm going to do is take a state here, map it into this factorized space, and then compute the ordinary entanglement entropy, the von Neumann entropy. But if I don't map it in a way which preserves the inner product, then I can just multiply the answer by 300 or whatever. So it better have this property. And then in quantum field theory, we usually require that this Hilbert spaces, the two cut sides, are defined by some Lorentz covariant boundary conditions. So I imagine I end the space at the entangling surface. So I have some region. The region has a boundary. And then I can look at the causal development of the region. So there's some null cone whose two null cones, future and past null cones, which are glued along the boundary of the region that I'm talking about. That's what I'm calling, that in the gravity case would be the extremal surface, but in quantum field theory it could be any surface that I draw, of course. And so when I want to cut the Hilbert space, I try to put some boundary conditions along that null boundary, or maybe I should slightly regularize, so pull in from the null boundary to make a time-like boundary that will asymptote. I'll take some limit that will make it go out to the null boundary. And on that boundary, I want to put some Lorentz covariant boundary condition. And I also want this map to respect locality in the sense that if I have a local operator that's completely in the left region, then its action on states here should get mapped to just this tensor factor. Okay, so now, of course, in continuum quantum field theory, there actually doesn't exist such maps. It's not possible to find such a map, and that's related to the fact that the entanglement entropy has divergences. So you need to regularize the story a little bit. So you introduce some regulator, which basically means that I'm making this cut finite instead of putting it exactly at the extremal boundary. And then, so I have some epsilon, and then this map becomes an isometry only in the limit that epsilon goes to 0. But if I try to take the epsilon goes to 0 limit first, I mean, the map doesn't exist. So the Hilbert space, the factor, this stops making sense. Okay, so that's where there are some divergences in quantum field theory. Okay. Now, to go back to this Chern-Simons example, because it's, I think, kind of a cute example, suppose we think about the Euclidean calculation of the Rayleigh entropies. So that's the trace of the reduced density matrix to the nth power. And if you knew the Rayleigh entropies, you could try to find the von Neumann entropy by the analytic extrapolation and the replica parameter. Right? So if we do the Euclidean calculation of the Rayleigh entropies, the regulator that I just described corresponds to excising a tubular neighborhood of the entangling line. It's an entangling line because I'm in 3 dimensions rather than a surface in 4 dimensions. And putting some boundary condition there. So here's the boundary of my region, and then around this line in Euclidean path integral, I cut out a little tube. So the boundary here looks like a torus in the Euclidean case. And that's nice because in the Rayleigh entropies, the actual manifold is singular, right? It has a 2 pi n conical angle around that line. And so if I cut the line out, then everything looks non-singular, but now I have this boundary condition. And I can also use the boundary condition to define the cutting map. So I do a little Euclidean path integration with the boundary pulled in Euclidean time, and that's a way of defining this cutting map, which is very nice. And then this unitarity condition implies that if I have a smooth line, not one where there's a conical defect, but just at a smooth place, and I excise it and with a tubular neighborhood and put this boundary condition, then in the limit that I pull it away, it doesn't do anything. So it inserts no line operator, if you like. Now, in Chern-Simons theory, if I want the Lorentz invariant boundary condition, I better pick something like A plus is 0, where A plus is the chiral component of the gauge field along this boundary. So there are 2 coordinates of this boundary. One of them is the direction along the entangling surface, and the other one is the replica time direction. So the natural boundary condition is something like A plus is 0. That's really the only gauge invariant and Lorentz invariant choice, roughly speaking. Anyway, it's A choice, and in the limit that epsilon goes to 0, this is really equivalent to just setting a tau to 0, where tau is the replica direction because the tau direction is becoming extremely small. So I go all the way around the tau loop before I get to move in the x direction because the size goes to 0. So it's pretty much, in the limit, it's the same as if I had set a tau to 0. And setting a tau to 0 is a very natural thing to do from this point of view because it just says that the holonomy around the edge of the region is 0. In other words, if I cut out a smooth line, the holonomy around it is 0. That's just the condition that it doesn't insert any line operator. So it's exactly this kind of shrinkable condition which obeys that unitarity constraint. Well, at least after you add some appropriate counter term related to the extrinsic curvature, which in this case of a two-dimensional boundary of a three-dimensional space looks like the circumference divided by the small length, epsilon, the narrow length of the tube. So, okay, so that was a lot of words, but then the actual calculation is extremely easy. So when I have this kind of boundary condition in Chern-Simons theory, it just gives me the chiral modes of the WZW model on the boundary. And in the case of the Abelian Chern-Simons theory at level k, that's even simpler. It's just the chiral boson where the periodicity is k. And in this limit, where we send epsilon to 0, it's like the torus partition function at infinite temperature, because I send one direction to 0. Or equivalently, if I had just taken the boundary condition to be a tau equals 0, I would have gotten the chiral WZW model Hilbert space, but 0 Hamiltonian, as been known for a long time, like work of Schwimmer and Seiberg and well, two other people who I unfortunately forgot their names, but they're well-known people. I know them, but I just don't remember who was on that particular paper. So I'm still half asleep. Okay, but anyway, so you get the chiral WZW model, but then there's also this counter term. So you get the entropy at infinite temperature minus this counter term. It's good you have the counter term because otherwise the answer would just be divergent. And it's extremely easy to compute the entropy. It's the log of the partition function. And so the partition function is just the product over all of the angular momentum modes, which is labeled by some integer I call little n, which ranges from 1 to infinity, of k. There's no n there, but okay, because in each mode I have k possible states. So the log of this is log k times the sum over 1, which is minus 1/2 when you add this regulator. So that's how you get the right answer. Okay, so I think this is an old story, but maybe I said it a little bit differently. But actually, I think it would be very interesting to understand whether in general quantum field theories, like not just in this topological case, if there is any dependence of the finite terms on the boundary conditions described here, boundary conditions of this type, once you impose this isometric condition. So of course, if you don't impose that, I get any answer. It's not the right calculation because I just multiply the state by 5. But if I impose the unitarity condition, it still seems interesting. I mean, it seems interesting to understand see if you could prove that the finite terms after making these kind of counter term subtractions really don't depend on this choice, or see if they do. So that's some work with Thomas Dimitrescu in progress also. Okay, so now let's come back to gravity, which is the main thing I wanted to talk about today. Time? 10 minutes? Okay. Okay, so the question is, can I apply this kind of logic to gravity? So is there a boundary condition that can excise the extremal point, because now I'm back in 2 dimensions, that obeys the shrinkability condition? But in gravity, this shrinkability condition, if it's possible to satisfy it, is actually extremely powerful, because in gravity, entanglement entropy is UV finite. I mean, ignoring bulk renormalization. There are no new counter terms that you have to add associated to the entangling surface. And that's because the Rényi partition functions are given by smooth saddles, smooth Euclidean saddles, which don't have conical excess angles. So because metric is dynamical, so it automatically removes and smooths out the conical excess angle. Faulkner, Lukowitz, and Maldacena used that to derive the Ryutaki-Yanagi formula, for instance. That derivation was interesting because then they quotiented by the ZN symmetry to make a conical angle, but it was important that in the original calculation, in the definition of the Rayleigh partition function, which has the n-fold cover of the boundary, this gravity saddle is smooth. That's why when you quotient by n, you get something which has a conical deficit. Anyway, that's not what I want to talk about here. So in the gravity case, you also shouldn't introduce some background metric on the fictitious boundary, so there wouldn't be any counter terms that you could add. And so if you do it right, it means that you just get the right answer. Of course, maybe that's an evidence that it will be hard to find this kind of boundary condition. But we'll see. So this is a work in progress with these two students of mine. Now, it's somewhat useful in this game to use the first order formalism for gravity. So the point is that here we shouldn't need to take a limit. You should be able to, here you should be able to take the limit and get the correct answer. Unlike in the QFT case where you have to compute the entanglement entropy first and then take the limit of the quantity. Here it seems that you should be able to take the limit at the level of the Hilbert space and then compute the entanglement entropy, because there are no UV divergences in the actual answer. And of course, that means that you're going to need some boundary condition which says that something like the boundary shrinks away. And so that's somewhat singular to describe in the metric variables. So that's why it's somewhat useful to use this first order formalism. So in the 2D dilettante gravity, 2D dilettante gravity can be reformulated as an SL2R BF theory. It's very similar to the way that pure 3D gravity can try to rewrite it as an SL2R times SL2R Jones-Hyman's theory. And the way it works is the action looks just like trace of phi f, where f is dA, or covariant to dA, where A is the SL2R gauge field, and phi is some SL2R adjoint field. And on shell, the way these new variables relate to the original dilettante gravity variables is that the so A runs from 1 to 2, and 1, 2, 3 are the three generators of SL2R. And so the two of the generators, so A1 and A2 are just given by the two components of the Zweibein, and A3 is the spin connection. And then the three component of this phi is the original dilettante, and the 1-2 components are this slightly funny looking combination, which involves some derivatives of the dilettante. And so the equations of motion here are extremely simple. They say that F is a flat connection and capital phi is covariantly constant. So for instance, the fact that F is a flat connection, two of the equations tell you that omega is the spin connection associated with that Zweibein. And then the third equation tells you that the curvature is given by -2, the Ricci curvature. And similarly for phi, the covariance constancy of capital phi is equivalent to the dilettante equation of motion of 2D gravity. So it's a, classically or perturbatively an exact reformulation. Now, and the nearly ADS2 boundary conditions are ones which fix the Zweibein, because you're supposed to fix the metric on the boundary, and phi 3, because that was the original dilettante. So you can redo everything in this first order language. It's neither, if you didn't want to introduce this extra fictitious boundary, it would be, I think, neither easier nor harder than the usual analysis. But just another way you could have done it. But a curious fact is that if you write the Euclidean black hole, that is the saddle of the 2D dilettante gravity with the disk topology, it actually cannot be written as a smooth flat connection on the disk. So it doesn't look like looks like something is wrong in the change variables between the dilettante gravity and this BF theory. And the reason is because on the disk, the Gauss-Bonnet invariant is supposed to equal 2 pi, so the integral of the curvature over the disk times this extrinsic curvature integral on the boundary. That should be 2 pi. But if I rewrite this combinations in terms of these variables, the first term gives me the integral of d omega, where omega is this particular component of the gauge field, and the boundary part gives me the integral of omega over the boundary. And so if omega makes sense on the disk, this is 0 and not 2 pi. So the answer is that somewhere in the interior of the disk, there has to be a singularity in the omega. So there's a point where the curvature sets someplace. So actually, exactly the same thing happens in Euclidean BTZ if you try to rewrite it in the Chern-Simons variables. And this abstraction is really topological in nature. So the theory reduces the theory of flat connections. So we can write the connection as G inverse dg for some group-valued guy G on the spacetime. So this is some gauge trivial thing. And then a smooth connection on the disk, of course, has trivial holonomy of G of so let's look at the boundary value of this guy G. So, and from that we could compute the gauge field, the time component of the gauge field, because that would be G inverse del T G. And so if we look at G of T, where T is the Euclidean time coordinate, which goes on a circle, G has to, when I go all the way around the circle, G comes back to itself. Well, that's true because the G is supposed to be well defined in the disk, and the circle is contractible in the disk. So it's supposed to have trivial holonomy. But not only that, it's supposed to have trivial homotopy in SL2R. And in the Euclidean version of this BF theory being related to 2D gravity, the spin connection direction is Euclidean, so it looks like an SO2 connection. So it's the compact circle in SL2R. And in fact, the nearly ADS2 boundary conditions require that it has holonomy winding number 1. So the holonomy is trivial, it goes around, it comes back to the same group element, but it wraps in a trivial pi 1 in SL2R. And that's inconsistent with it being a connection on the disk. So actually, if you really wanted to use this first order formalism, you sort of need, and we want it anyway, to introduce some inner boundary. So you cut out the bad point, basically, in the interior, and that allows this G of T to have winding number 1. And having winding number 1 around the little point in the interior corresponds to having no conical angle at the excise point. More generally, if I had this guy have, so in general, this guy doesn't, now I have something on the topology of an annulus, and so then this G doesn't have to be single valued, it can have a holonomy as I go around, and the total integral around is, the difference from 1 is exactly the conical angle of the part that I cut out. Now, one way to proceed here is to allow a classical center. So to generalize a little bit this factorization of the Hilbert space that I mentioned. So instead of trying to map the Hilbert space into a factorized one, sometimes people introduce some classical center variables where I have some center variables labeled by n, and then I take a tensor sum over a series of factorized Hilbert spaces. So it's like factorization with superselection sectors. But actually, if n was a discrete variable, I could always embed this guy into this one, which does factorize, of course. So it's really only in the case that n is a continuous variable that this guy might not make sense. And in that case, it's a true generalization. Otherwise, I can swallow it back into the story that without including the center. In other words, I can just say that the density matrix looks block diagonal in a bigger Hilbert space. But if I have to do some integral, I might not be able to do that. So in the case where I have to do an integral, I have this center variable x, and then I get a factorized Hilbert space for each x. I compute some rho x. If I want to compute the jth Rényi entropy, I take the trace of rho x to the j, and then I multiply it by some function of x and do an integral. So that's like some weight, the classical weight function of this center variables. Now, in the 2D dilettante gravity, at the inner boundary, it might be natural to try to fix the dilaton as one of these center variables. And then in this first order language, that I would set say, the phi 1 and phi 2 to 0, which turns out to imply that the boundary shrinks to the extremal point. And I also set the value at the extremal point. So in general, that forces there to be a cone angle, because if I have a certain length of the nearly ADS2 boundary, and I demand that a particular value of phi demand a particular value of phi to be the extremal value, I'm forced to have a cone angle there because it won't match the smooth saddle. And so then to reproduce the Euclidean answer, you're supposed to integrate over the center variables weighted by the action of the missing part of the space, which is the integral of square root gr times phi in the interior. And then there's also this background term with some phi naught, which is a constant. Now, and in addition, in the Jacquier-Teitelbaum term, I should have put r plus 2. But because this integral is over an infinitesimally small region, the part with the plus 2 doesn't contribute, because the integral of square root g over the tiny region is 0. But because there's a cone angle, r has a divergence, and so that piece gives me something finite, so I get this combination. And then, of course, I can just use the Gauss-Bonnet theorem to rewrite this in this way. So it looks like 2 pi minus this piece. So this piece I can add to the boundary. It's part of the boundary action, but this 2 pi looks funny. It looks non-local, right? It's not given here by the integral of something over the boundary. It's just a pure number. So that's the classical weighting of this center variable. So the Lorentzian classical solution is just unique here. So it's just the black hole with a given value of phi h. Am I almost done? I'm almost done. Yeah. So it would be the black hole with a given value of phi h. And so its energy, which is only the energy from one boundary, is phi h squared over phi b. And so if I plug that into this formula, I get this Gaussian integral, which actually gives the correct leading order entropy. But this isn't very satisfying because it seems that I mostly put in the answer by hand through this weight factor. Now, if you wanted a more quantum mechanical treatment, somehow you should treat the dilaton quantum mechanically and impose instead a boundary condition on the spin connection instead of fixing the dilaton and then classically integrating. So this is like trying to fold the sum over the center variables into actually factorized Hilbert space. And so you could try to set the spin connection to be the derivative of some scalar, which is periodic. And then the sum over the scalar will give you a sum over integer winding numbers, which means integer cone angles, 2 pi times an integer, that at least includes the value 1. And the guy with winding number 0 is not a solution because it's not compatible with the ADS boundary conditions. So you might hope that the guy with winding number 1 dominates. And this whole thing is a theory of flat connections. So everything just reduces to this group variable as a function of time on the inner and the ADS2 boundaries, and they're completely independent up to the fact that they have to be homotopic in the group. And the goal is to find the boundary condition on the inner boundary so that the inner boundary integral over G just gives 1. And, well, we haven't finished yet, so that's why this talk is still half-baked, but it's actually automatic that the inner boundary path integral doesn't depend on beta because beta is about the length of the ADS boundary. It doesn't even enter into this definition of the inner boundary, so it might seem easy to get it to be 1 because if it doesn't depend on beta, it's just a pure number. But the challenge is really to find appropriate boundary degrees of freedom or choice of contour in the path integral so that the Lorentzian continuation is well defined and that winding number 1 dominates, so you don't end up saying that, yeah. Okay, so I'm almost finished. So let me just say one other slightly different thing. So you could also ask, how could you define the entanglement entropy in string theory? How would you cut spacetime in string theory? And I mean, one interesting idea is to again look at the Euclidean version, Euclidean story. So if we look at the 2D Euclidean black hole, it's like the cigar string theory now. And then That's doable by the Fateyev-Zamolodchikov duality to the Sine-Liouville theory, where you have some potential for the Euclidean time winding. And in the 2D Euclidean black hole, the time circle shrinks, but in this theory, it doesn't. So it looks like an analog of the low-energy gravity story that I was trying to develop. So if you knew the Lorentzian continuation of the Sine-Liouville theory, it would give some entangled state in a factorized Hilbert space of microstates, all described by weakly coupled strings. And if you knew that, it would be a situation in which ER equals EPR was given by some string duality. So it would be some microscopic bulk explanation. But we don't know what's this analytic continuation. Maybe there's a sense, especially in some examples with ADS boundary conditions, that you could just take the Lorentzian continuation of the boundary correlators to be the definition, and then this would already be established. But maybe we need to understand the Lorentzian thing a little more. So just to wrap it all together, obviously the low-energy gravity story that I was describing, where you put this boundary condition, isn't expected to give the exact spectrum of microstates. It won't give you these microstates. That wouldn't make any sense. But the hope is that, at least in perturbation theory, you might be able to correctly capture just the entanglement entropy by some effective bulk variables that live at the entanglement horizon. So for instance, if you looked at this Sine-Liouville example, is there some target space effective theory approximation to the Sine-Liouville way of calculating this 2D gravity partition function? And that would really be exactly what we're looking for here. So we shall see. So thanks for listening.
Questions?
Mm-hmm. Just a small comment. So the duality between the black hole and the Sine-Liouville string theory, you have to do the T-duality of the time circle. So then the Lorentzian continuation of one and the other seem to be rather different.
Right. So
you can certainly do the Lorentzian continuation of one, and one gives you a black hole, and the other one gives you some spacetime that doesn't have a black hole. But I don't know that there is a duality between these two Lorentzian continuations. They are two different.
Right. So by the Sine-Liouville, I meant the guy where you didn't do that T-duality. So in other words, on one side you have the Euclidean black hole. The other side I have the Liouville potential for the radial direction, and then sine of the winding guy of the other direction. And then I do the Euclidean. Then I try to do the Lorentzian continuation. But of course, I don't know how to do that. That's why that's perhaps why we don't know how to do the Lorentzian continuation. Right?
If you are in two dimensions, of course, when you excise the central point, you basically break space-time up into two halves,
Yes.
And you can do anything you like there. Basically, the question how to connect them back together there.
Right.
But this Monday in the school, I'm going to discuss the 3D black hole, and there the answer to the question is what you have to do is you have to include the interactions between in and outgoing particles. So in and outgoing particles cannot be considered as free particles, because the one interaction you definitely cannot ignore is the gravitational one. So gravitationally in and outgoing particles interact, and that causes things to flow over from one side to the other side of that space-time. So now you can no longer excise a central point. And now there is a well-defined prescription as to how to make the whole thing unitary, because that's the big question is how to make all interactions describe some effective object where the interactions are unitary, so that you can switch, you can add it to all other things you know about the physical world as an extra particle with a unitary scattering matrix.
Yeah, thanks for the comment. And to clarify, do you have in mind a single-sided, like a black hole with one asymptotic boundary in a pure state, or the two-sided black hole with two asymptotic regions?
Well, that's exactly the point. So now you have to, first of all, you have to decide what to do about this. There are two asymptotic regions, and my answer is the only correct way to do this is to identify both sides of being the same black hole. But the 1 degree of freedom you still play with is where on the horizon are you sitting? And there's exactly one answer that works, and that's that the other side of this asymptotic, the other asymptotic domain of the black hole describes the untitled points of the radio.
Yes, okay. Yeah,
So you just,
okay.
you just go to the other side.
But I think
that's the only way it works. If you do anything else, you don't get the unitary description.
I think you're trying to solve a harder problem of how do you understand the entropy of an ordinary black hole. Here I wanted there to be two asymptotic regions so that I could think of the entropy as an entanglement entropy. But indeed, in the situation you're talking about, where you sort of quotient or orbifold the space, so you have one boundary, then then I see why you say there are these interactions. But that sounds like it's that sounds harder, more ambitious than what I was trying to do.
Well, yes, but if you don't ask this question, it's not basically anything you can do. I mean, it's not a God-given thing what a two-dimensional universe looks like, because we're not in 2 dimensions. So you can think of all sorts of possible answers to the questions you're asking. You might factor out at center point, but then you lose the ability to compute anything like Hawking radiation or temperature. And you can play around with the boundary conditions any way you like, because you invented your own universe. And you can play around with it any way you like. So to ask how does nature solve the problem, you have to go to the real world. And then again ask these questions. And my claim is there is one good answer and many wrong ones. One thing that's quite far in this respect, if you include the interactions in the upward particles.
Sounds interesting.
Let's thank again Daniel.